Okay, so this is the data reduction video for the third lab for the beam. So this will be pretty standard to what we've been doing so far for the first two labs. I'll be doing the data reduction in this kind of weird looking window, which is still MATLAB. I just prefer this. So in this window here, we have the script, and then down here is the command prompt that you would have in MATLAB. Alright, so this time the first thing that we're doing is specifying where our file is for the data that we have. So I'm going to go over this part just because I think there's been some confusion on the syntax that I have here. So I'm going to go to my folder. Let's get a more traditional looking file manager just so it's easier to understand. Okay, so let's go to my documents. Also, I noticed that a lot of you don't store your files very well. Like, you put it in your downloads folder or something. And I'm not judging you too much, because I did that too before. But trust me, if you have all of your schoolwork in your downloads folder, it's going to be a huge pain in the ass as you continue on in undergrad. It's going to suck. So do yourself a favor and store your stuff a bit better, right? Have a folder for each class at the very minimum. Very least. Okay. So let's go to the folder that I have for our class. And I'll go into experiments, data reduction, experiment 3. So right here, this is where my script is right now. So that's the script that you see here. I'm in this folder, which is called experiment 3 beam. But my data is in a different folder. So my data is actually going back 2 directories. So I'm going to go back 1 directory into data reduction and then 1 more directory into experiments. So we're going back 2 directories, and that's signified by these 2 things here. So these 2 dots and a / means to go back 1 directory. And I want to go back 1 more directory, so we're going to go into this experiments folder. So I'll click on that. And then I'm saying to go into my data folder, so data, and then Thursday 8:30, and then lab 3, there's a space in this folder name here. MATLAB sometimes doesn't like spaces, by the way, but in this case, it was okay. And then I'm going into team deadweight.xlsx. Okay, so that's how I am specifying the location for this folder. You could have the folder in the same folder, or you can have your data in the same folder as your script if you want. No, that's totally fine. So let's say that I had the data in the same folder as my script. If that was the case, then I would just take all of this out. Let's redo it. So if the data was in the same folder as our script, all I would have to do is team deadweight.xlsx. I like to store the data in a different folder though, so that's why we need to do all of this here. Alright, so hopefully that clears some of that stuff up. And now let's take a look at our data that we have. So let me go over here. So I got this from one of my groups on Thursday, so hopefully you set up your Excel sheet somewhat like this. So they have 3 different sheets for their different tests that they ran. And they also have a sheet for the dimensions, so that's all of that right here. So I told a lot of you to have your first 3 sheets for the trials, and then have your 4th sheet for the dimensions. When I did this data reduction, this particular group, they have their dimensions on the 1st sheet. I could have moved that to the 4th sheet, but I didn't, and I don't really feel like changing it. So anyways, just keep that in mind. You might have yours, your Excel file set up a bit differently. Okay, so let's go back. Okay, so we have that, and just like last time, we need to define this variable called ops here, and that's going to be equal to, or it's going to be assigned really to detect import options, and then we're running this function on our file for the data that we have. And I opened that up over here for what ops is actually containing. The area of interest for us is going to be sheet, because we want to import those last 3 sheets that we have. which is the data. So for this part, I'll leave this to you guys. This is just your geometric data. So what we need is the height, we need the base, we need our S value, our D value, and then also I've defined Y, which is the distance from our neutral axis, which if you remember from the lecture, is the height divided by 2, because the neutral axis goes through our centroid. We have our elastic modulus, so it depends on what source that you use for the published value. For this lab, I'm going to use 29,700 multiplied by 10 to the third. That's in units of PSI. So let's add in a little comment there. Really, I probably should have put the units for every single line here, but it's an English unit, so the dimensions are in units of inches. Elastic modulus in units of PSI. And then A is our section, so that's 4 inches long. And then L, that's our length, that's 12 inches. Then we have our moment of inertia, which is provided on the deliverables handout. So it's 1 divided by 12 multiplied by the base times the height cubed. And then we're subtracting those kind of two kind of like phantom rectangles that we have. And then we can calculate our moment of inertia. So just to kind of recap that, let's go over here. Let's open the deliverables up here. Let's go on a different tab, actually. Okay, so the deliverables, we have our moment of inertia down here. So we have all of these dimensions, our height, our base, S, and then D. And the equation for it is right here. So all I did is I plugged that into MATLAB. Okay, so here we are. So make sure that you calculate your moment of inertia. For reference, it should be around this. So we have 0.0716 inches to the fourth, I think, right? I always forget if it's inches cubed or inches to the fourth. Yeah, it's inches to the fourth because we have base times height cubed. All right, so there you go. So that's all of the kind of preliminary stuff that we need. And now we're actually going to run through our loop, which we're going to have for our calculations and then our plots. Okay, sorry, looking on my phone. So the first thing that we got to do is actually import our data. So far we've told MATLAB where the file is stored, but we haven't actually imported anything yet. So we got to do that. So what I'm going to do is for n equals 2 to 4, you can use, any letter. You could do for I, whatever you want. I'll do for n equals 2 to 4. That's our counter variable. And I'm doing 2 to 4 because I'm importing sheets 2, 3, and 4. That's for my case. For you, it might be different. So let's go back to our data. For me, the 3 different tests that we have are in sheets 2, 3, and 4. For you, it might be different. It might be like sheets 1, 2, and 3. So if your data for each test is on 1, 2, and 3 for the sheets, then you're going to have for n equals 1 to 3. Okay, so we have for n equals 2 to 4, and now we're going to tell MATLAB the sheets that we want to import. So again, we're going to be referencing ops, which is that variable that we created right here. So let's make a little comment, sheets to import, and we're going to put ops.sheet. So this is accessing the properties that we have for ops, which is opened over here. You see sheet is one of the properties, and we'll set that equal to n, because again, we want to import sheets 2, 3, and 4 for my case. All right, now we actually want to import the data. So we know where the file is and we know what sheets that we want to import. So now let's actually import that data. So I'll call this data. We're going to use read matrix, and then we're going to say file name. That's the very first thing that we defined up here with the file name where that is stored or located. So we have file name, then comma. Here we're gonna have an argument called sheet. And now we actually need to say what sheets we want to import. So we'll say n. So thinking about this now, I actually don't even need that line. I should have deleted that. So we'll put n. And now we're going to say what range we want. And well, I'm going to say A2 to C11. So again, this is for my case. Let's go back to our Excel sheet. For our data here, we want to import the data from A2 to C11. So all of these numbers here, this kind of matrix. Okay, so A2 is this cell here, and then C11 is this cell here. And all of our three sheets that we're importing, they're all formatted the same. So each of those sheets has data from A2 to C11. Okay, so we'll import that. And now I can open up data in our workspace over here, and you can see that we have our data. So because I'm not actually saving all of the data here in something like, let's say, a cell array or a multi-dimensional array. What you see here for data, that's the third pass. So that's the data for our third trial. Let's unsuppress this. I'll run it now, and you'll see in our command window that it shows all of the three passes in our loop. So all of this here is the data for the first test, then all of the data for the second test, and then the third test. We can look at the numbers a bit better by doing format short G, and then we'll run our script again, and now you can see that that the data does change a bit. You know, it's very similar, but if we're looking at like the last column here, which is for the strain gauge, you can see that these values are a bit different. The dial gauge, from what I've seen, is very similar throughout. You can see here the first value is a bit different. And yeah. And I'm thinking about this right now. I didn't notice this before, but for the group that I got this data from, you guys are going to want to go back and edit your load here. Because, you know, in reality, your load was not exactly 100. It wasn't exactly 200. It was probably, you know, 100.3 something. Or maybe it was 101 point something when you paused your video. So, you know, what I mean is when you might do your very best to pause it at 100 pounds, but on the screen for what you recorded, it was actually probably 100.3 pounds or something like that. So you should go back and edit this, because what this is doing right now is just adding even more error to what you have. Alright, so yeah, we want to make sure that you guys fix that part. And of course, anyone else that did the same thing. Alright, so we have all of our data, and now let's actually do some calculations. So the first thing is the bending moment. And if you remember from our lecture, the bending moment is our load divided by 2 multiplied by A, where A is the kind of section that we have. I just want to provide more context this time around, so I'll actually open up our lecture that we had. Okay, so in our lecture, let's go to the very top. We have these 3 different sections for A. So the length of the beam is 12 inches in each section here. A is 4 inches. For us, we're looking at this middle section because that's where the maximum bending stress is going to occur. And we're in pure bending in this middle section here. Okay, so again, the moment is the load P divided by 2 multiplied by A. So let's calculate that. So this is going to change, you know, throughout the test because the load is increasing. So we're going to have this in our loop here. So we'll have moment equals data, all of the rows in the very first column divided by 2 and multiplied by A. Okay, so here I have array addressing for data. So I'm getting all of the rows in the very first column because that's our load. We'll go back to our sheet, you see we have all of the rows in the very first column. That's for the load. So we want to get that column there. Okay, so we have our load divided by 2 multiplied by A. And there we go. There is our bending moment. Next thing is going to be the theoretical vertical deflection. So we had a formula for that as well. So we'll call this deflection theo. That's equal to 23. So I'm going to put our numerator in parentheses here. So we have 23. You know what I'll do? Let's go back over here. Okay. Put this here. Let's go to our, all of the important formulas are on the deliverables as well. So anyways, the theoretical maximum vertical deflection is 23 multiplied by the load multiplied by the length cubed, all divided by 1,296 multiplied by the elastic modulus in the moment of inertia. Alright, so let's plug all of that in. We have 23 multiplied by the load. So for my case, that's data, all of the rows in the very first column. And then multiplied by the length of the beam cubed. Okay, that's our numerator. Now let's divide this by the denominator. That's 1,296 multiplied by our elastic modulus. We're using the published value, so we're not calculating that for this experiment. So we'll just use the published value, so that's E. And then moment of inertia, because this is our theoretical calculation. So we're still using the load that we had in the experiment, but we're going to be using the published value for the elastic modulus. And then we're using the moment of inertia that we calculated. It's kind of weird. Okay, there we go. So there's our theoretical vertical deflection. Alright, now let's do our experimental vertical deflection. Well, there's nothing to do here. We recorded that directly, but I'll just make a comment here. That's, for my case, that's the second column in the spreadsheet that I have. Spreadsheet. So that's this column here for me. That's what this group recorded for the dial gauge. Alright, next thing is going to be the experimental bending stress. And we have a formula for that as well. Experimental bending stress is here. So our experimental bending stress is going to be the elastic modulus that we have. We're using the published value again. And we're going to be multiplying that by the strain that we got from the strain gauge. And remember, the strain gauge is in units of microstrain in LabVIEW, so we need to multiply that by 10 to the negative 6 to get units of inch per inch. So we'll call this bend stress experimental, and this is going to be our elastic modulus. I'm going to write it this way right now. So our elastic modulus multiplied by the strain from the strain gauge. And then for me, the data for the strain gauge is in column 3. So I'm going to say data, all of the rows in column 3, multiply that by 10 to the negative 6. And now we're going to be in units of PSI. So we'll go back to our data. This column here called strain, that's from the strain gauge. So there we go. There's our experimental bending stress. Now let's do our theoretical bending stress. And then again, we have a formula for that. That's going to be our moment, our bending moment, multiplied by y, which is the distance from the neutral axis, divided by the moment of inertia. Okay. Yeah, okay, cool. I was just seeing in my script over here if I used our variable here, which I should have, and I did. So we'll call this bend stress theo, and we'll set this equal to the moment, which we calculated up here, So our bending moment multiplied by y, which is the distance from the neutral axis, so multiplied by y, and we defined that up here, just the height divided by 2, and then we're going to divide that by I, the moment of inertia, which we also calculated up top. Just to be clear, we could put the numerator in parentheses, but in this case it's not going to matter. Okay, so there we go. We got the theoretical bending stress. Alright, so now we've calculated everything now. So we can go ahead and calculate our percent error, and then we can make our plots. Alright, so let's go ahead and do that. Let's do our percent error first. We'll do it for the theoretical deflection. So I'll actually show you guys how to do the percent error this time. It's a very basic formula, but I'll just show you this time. Why not? Okay, so we'll do deflection error. We're going to have our absolute value. Okay, you need to take the absolute value because you're not going to have a negative error. That doesn't make sense. So we have our absolute value of what we calculated. So that's gonna be data. All of the rows in the second column for my spreadsheet, because that's the second column is the deflection. Subtract that by deflection theo, and then we're going to divide that by deflection theo, and then we're going to multiply all of this by 100. Let's unsuppress it for now, just so we can see all of we can see the percent error for all of the 3 trials here. Yeah, okay. So right now we have a matrix. Basically we did matrix division. You need to change this. So if you look at the deliverables, let me open them up. So if you look at the deliverables for this lab, or for this memo, you see that I say here to use the maximum value. So use basically the last value that you have. Okay, that's what we're going to be using for the percent error. Right, so I need to change this. And this will also give us a scalar answer, not a matrix. We want a scalar. So I don't want to get all of the rows. I want to get the very last one. So that very last value for the deflection. And then same thing for our theoretical deflection. We want to get the very last value. And we'll go over here and put end as well. And there we go. Now we have a scalar for each test that we have. In this case, they're actually all the exact same. Because if you look at our data, let's go to it. Look at our data here. Look at this very last value. Okay, right here. It's the same for all of the tests. Yours might be different for the 3 different tests, but for the data that I'm using, it was the same. So the percent error for each test is actually the same. So we'll say 0.8%, which is damn good. Very nice. Okay, now we got the percent error for the bending stress. And then again, we're using the maximum value. So we'll call this, what I call it, bending stress error. We're going to use the absolute value. Bend stress experimental. And then again, we want the very last value, so let's do end. That'll get the last one. Subtract that from bend stress theo. Stress theo, very last one. And then we're going to divide that by bend stress theo, very last one. Multiply it by 100 so we get a percentage. And this is pretty high. It's historically, it's been pretty high from the past labs that I've taught for this, and even when I took it too, right? Pretty high, we're right around 25% basically, so it is pretty high. But if you remember in the lab, either yesterday or today, depending on when you took it. Hopefully I talked to you about how there's a lot of chances for error that's going on here. The main thing is that you're taking a sample and you're measuring all of the dimensions on that sample, which is different than the material that you're actually testing in the lab. And someone else brought up a very good point too. We're looking at the stress and the deflection in that very center section of the beam. So we would have to measure that geometry at that specific section of the beam. Not anywhere else in the beam, but that very specific section, which we didn't do. So there's a lot of error there. And in our equations, we're assuming that the beam that we have is completely, totally symmetric. But if you looked at that sample that we had in class, it's not symmetric at all. It's pretty bad. And so, because it's not totally symmetric, there's going to be error from that as well. And then you have other things, right? So you have the strain gauge that we have. That was affected by temperature, especially for the lab that we had today, which was on Friday. Because of the rain, there's more humidity. That's affecting the reading that we get on the strain gauge. So you have temperature effects as well. And then another big source of error is the accuracy for your call out. So remember, you had someone that was calling out 100 pounds, 200 pounds, up to 1,000 pounds, and that was kind of being relayed for the deflection. So that's error for the deflection part, but for the bending stress part, yeah, you're recording the video as best you can for intervals of 100 pounds, but it's not going to be exactly in intervals of 100 pounds. So there's some error there, but it's not as bad because you're looking at just the load and the strain gauge for that, and that's all on one screen for the person that was recording that. But either way, there's a lot of different sources of error that we have for this lab. So, those are just some of the things that I thought of on the top of my head, but, there's more, right? So think about them yourself and talk about that in your report. So again, this is pretty high, but unfortunately, it's kind of typical, or maybe fortunately, however you want to think about it. But yeah, 25% error, pretty high, but it's typical for what we've had in this lab in semesters past. Alright, so now we're going to be on to the plots. So I'll just make one for the deflection versus the load. So deflection versus load. But this time, I'll actually have you do the other one by yourself. So if you look at the deliverables, we need... No, those are my notes. Did I close out of them? Okay, the deliverables, you need plots for the deflection versus load, which I'll show right now. And you also need plots for the bending stress versus load. So I'll have you do that one on your own. It's going to follow basically the same logic that we have for the deflection versus load. So, don't worry about it too much. But I want you to do that part on your own. Okay, so we're going to assign a variable here, just like we did last time. So I'll call this fig_d for deflection. And we're going to have 3 figures here. So I'm going to call this figure n. So for each pass, we're going to create 1 figure, and then 2 figures, and then 3. Really, it's going to be called figure 2, figure 3, and then figure 4. And then I'll do fig_d.position. This is for the size of our plots. Do 0, 0, 750, 500. That's just typically what I personally use. You can do something else though. fig_d.visible. We're gonna have this on right now because I want to see the graphs. And now let's actually plot it. So for the x argument, we need the load. So let's do data, all of the rows in the first column, and the second argument is going to be our deflection. So that's going to be on the y-axis. So let's get that. We'll do the experimental one first. So that'll be data, all of the rows in the second column. Again, this is for me. This is for the Excel sheet that I have. Yours may or may not be the same. Okay, we'll make this a red line, and we'll change the line width to 2. And let's just run this one right now. So here we go. Here are our plots. They're basically going to look like exactly the same. And something that I should have done in the second data reduction video, but I didn't, and I should have. You know, we have this solid line here, which is implying that we have a lot of data points. But we don't. We only have 10 data points for this lab. So we should actually indicate that in our graph. So what I'll add on here is a dash, which is going to indicate a line, and then an O, which will be data markers for all of our data points. So let's run that again. And now you see that we have those circles, which again, they indicate the data points that we have. Alright, so that's better, because again, we only have 10 data points. That's not much, so we should actually show that in the graphs that we have. Oops. I guess you probably just saw the code for the making the plot for the bending stress. Whatever, not a huge deal. Okay, so we got that. Now let's add a little comment here. That was the experimental, and now we need the theoretical plot. So we'll do hold on and then plot. We need the load, so that's all of the rows in the first column. And now we're going to put our theoretical vertical deflection. So we called that deflection theo. And here, let's make this blue. And again, we're going to use a line with data markers of circles. And then we'll change the line width to 2. And this will be our theoretical plot. Theoretical. Then we'll do hold off. Let's run that. And you see that for the vertical deflection, remember we had a percent error of, it was like 0.8% for the very last data point. So this is a really good plot here. It should be accurate for everyone for the vertical deflection. The bending stress is when you're going to see a percent error of around like 20%. Probably like 10 to 20% really. This one is actually a bit high, not saying that this group did anything wrong. It might be just because of the load here. Because again, highly unlikely that it was actually, you know, exactly 100 pounds. It's probably 100.23, whatever it might be. Which won't change our percent error too much, but it'll change it a bit. Most likely, it's so high in this case because of that sample that we're measuring. Those dimensions are different than the dimensions of the beam that we're actually testing. Alright, so let's add on some other stuff. We'll do the legend. So first argument is the first thing that we plotted. That was the experimental stuff. Second one is the theoretical stuff that we plotted. Okay, let's do our X label. We have our load, that's in pound force. We have our Y label. Yeah, okay, is our deflection, and that's in inches. And then we have our title. So we're going to do our title just like last time where we say whatever the title is, in this case, vertical deflection versus load. And then we'll say comma, trial, and then it should say either trial 1, trial 2, or trial 3. So to do this, we need to use our square brackets, and then we'll say vertical deflection versus load, and then comma trial. We'll have a space in between, num2 string, and for me, I'm gonna put n-1, because remember my counter is for n equals 2 to 4, because those were the sheets that I had for the data. It was sheets 2, 3, and 4 for all of the data that we collected in the lab. But I want our title to say trial 1, 2, and 3, so I'm gonna put num2 string n-1, so that's gonna be, on the first loop, 2 minus 1 is 1. Second loop, 3 minus 1, 2. Third loop, 4 minus 1, 3. So there we go, and then we're going to do .png. Sorry, not .png yet. I was thinking about the next line, which is going to be for exporting our graphics. So we can run this now, and we should have everything looking good. Actually, not quite. We got to change the location of the legend. So by default, the legend goes in the northeast corner. Let's move it to the southeast corner, so it's not covering our plot. So we'll go here, and we'll change position. Or is it location? I always forget. I think it's location, but let's check. Yeah. Okay, so location, there we go. And now it's good. So now our location for the legend is in the southeast corner. That's good. And then let's export our graphics here. So export graphics, I can change this to GCA because I didn't define AX equals GCA. I can just type in GCA here, which again stands for get current axis. We need that to export our figures here. And we need our brackets again. So let's put in brackets here. We got brackets, and then over here. And I'm gonna put this in my folder that I have called figures. So let's show this again. Let's go to where the script is. Okay, so our script is here, and you see in this directory I have a folder called figures, so I want to save it in here. I'll make a whole, nah, I won't make a new folder. I'll just save it in here. Okay, so I'll call this vid deflection, because these are our deflection graphs. So vid deflection, we'll close that out there, and I want this to say, whether it's trial 1, 2, or 3, so we're going to use num2 string once again, and n-1, so it says 1, 2, or 3. And then we'll have this part here for .png, and there we go. So now in here, in my figures folder, once I run the script, I should see 3 new figures that say vid underscore deflection 1, 2, 3. I'm going to put another underscore right here. Okay, we ran it. Okay, it saved all of our files. And there we go, we have our 3 graphs right here. You saw the dimensions, they're kind of changing. That's an issue for my current setup using Linux because of this window manager that I'm using. If you're on, PC or Mac, all of your figures should actually be the same size. This is a bug that I just gotta fix. Alright, so there we go. So we got our 3 graphs, so we're good to go for that. And then I'll just show you what your bending stress versus load graph is going to look like. So again, these, I kind of have weird looking dimensions here, and I should have put this legend in the southeast corner like we just did. But your graphs are going to look something like this. Hopefully it's a bit better. But yeah, the percent error is going to be like 10 to 20%, something around there. Okay, so you have a bigger spread, unfortunately. You see in the beginning we're okay. And this is actually something that I would like you guys to talk about too. It's a good thing to talk about. Think about yourself why the percent error is not as bad in the beginning as it is at the end. You see it's increasing basically the entire time. The percent error is increasing. Alright, so think about that. That's a nice thing to talk about in the report. Alright, so again, I'll keep the second graph for you to do. It's going to follow the same logic as our deflection graphs here. You just got to change, some of this stuff up here. Call it something else like fig underscore b for bending. And then obviously you got to change what you're actually plotting. You're plotting the bending stress, not the vertical deflection. Let's see, there is another thing I could show you, but I'm not sure if I remember it off the top of my head. It's changing our formatting here for our labels to be in the format of LaTeX. And really it's useful if we have like a fraction or like a complex equation that we want to type out, but I don't know, let's just see off the cuff if I remember it. So we'll go over here. I don't think I'm going to. Just because you need to specify the interpreter that you have, which in this case will be LaTeX. But I forget where we put these apostrophes for the LaTeX formatting. Let's see. So what I'll do, I'll delete all this. I'll do \left. That'll be our left parentheses. We have pound. I'll do _F for pound force. \right. That's our right parentheses. Interpreter is going to be LaTeX. It's not looking good. Let's see if it works now. No, okay, so I'm forgetting the syntax for it. Okay. I didn't put $signs. So in LaTeX, which I might make a video for sometime, if you're in what's called math mode, so if you're typing out an equation, for math mode, you kind of signify that with $signs. Okay, let's move this back over. Aha, okay, there we go. Now it's working. So you see on our x-axis here, it's kind of small. I can increase the font size. It looks a bit different than our deflection here. And you see that we have a subscript for the F for pound force. This is just, for mostly cosmetics. So you don't need to do it for the report, certainly not. Font size, I think it needs to be capitalized like that. And then we'll do 14. Okay, there we go. So now our font size is bigger, so you can read that a bit better. But again, LaTeX, or that formatting, is more beneficial for when we have like a fraction or some complex equation. So let me pull this up again. So let's pretend that this was the bending stress graph, let's say. Or not really. I'm just going to show you how to type out a fraction. Okay. All of this is now superfluous. Is that the word? I don't know. So let's pretend that our x-axis was stress, which of course it's not, but let's just pretend. So we'll say stress. We need to be in math mode. And let's say \left, that we want this in parentheses. And this is going to be \right for the right parentheses. And then we would have a fraction. So in our numerator, if we were doing like PSI, we would have pound force. And then in the denominator, in a different set of curly brackets, we would have inches squared. And we got to close this out with $signs. So in this pretend scenario where the x-axis is stress, there you go. You see that we have this this fraction. All right, closed out of the video by accident, so you can't see me. Oh well. So that's the lab, all right? That's the data reduction for this time around. If you have any questions, let me know. I'll be in Discord. And that's that, alright? I'll see you later. Goodbye. Good night.